Okay, so we're going to start talking about finding volumes of three-dimensional shapes using calculus, using integrals. So the first thing we want to think about are cylinders. Now, when you think the word cylinder, you think what's called a circular right cylinder. Technically, in math, in higher levels of math, a cylinder is any shape made up of parallel lines connecting two parallel planes, which is a little different than the definition you see here. This is an equivalent definition. A cylinder is made by taking a shape and translating it from one plane to a parallel plane. So let me come down here and talk about generalized cylinders. So if I have any shape here, it really doesn't matter what it looks like. And I have that exact same shape. I'm going to try to copy and paste this. I have that exact same shape on a parallel plane, and then I connect it with a bunch of parallel lines. So well, these are all supposed to be, I know they're not very good looking lines, but they're all supposed to be parallel lines. So this shape I've drawn here happens to be a right cylinder, and then like on the back here, so these red lines are supposed to be the back. This would might be what we would call a right cylinder because all of these parallel lines here are perpendicular to my original plane, but it doesn't have to be. I could have just as easily taken this shape here and moved it over here and connected these two identical shapes through lines that go like this. Oh, I totally missed. And so forth. Now, the key here, what makes this a cylinder is this volume here that exists in between these two parallel shapes, made up of all of these parallel lines around the border. This volume has the same exact area shape all the way through. It's like we took this guy here and we just dragged it from one spot to the other. And then the volume we're talking about is that volume made up of all the little slices of this guy all the way up. Now, why do we care about this? Why are we talking about cylinders? Because for any generalized cylinder, the volume is always the area of the base, the area of the shape, times the height. And by height, we mean the perpendicular distance between these two planes. So height is this distance here, not this distance. We would call that the slant height, the perpendicular distance between the planes. The volume of any cylinder is area of the base times the height. So a cylinder is any shape, any volume that takes a shape and just moves that through space and keeps the same exact shape all the way through. So this would be a half right circular cylinder, but it's still a cylinder. And it's just a semicircle moved through space. So the cross section always has the same shape. Now, again, why do we care about this? Because this entire volume is always going to be, no matter what this cross-sectional shape looks like, the volume is the area of this base multiplied by this height. Volume of a generalized cylinder is area of the shape you're moving times the height, even if it doesn't go perpendicular along your axis here. Okay, we're going to use that fact to find volumes of objects that are not cylinders. This is not a cylinder, even though it's a trapezoid all the way through. It's not the same trapezoid. That trapezoid is getting smaller. We would need this to be the exact same trapezoid all the way through. A cylinder can't get bigger or smaller. But what we're going to do is use calculus, Riemann sums, differentials, and cylinders to find the volume of shapes that are weird like this. So what we're going to do is we're going to break this guy up into little pieces. So in this case, we've broken him up into 3 pieces. And this distance here we'll call delta x. If delta x is small enough, if this distance is small enough, then this thing kind of looks like a cylinder. This trapezoid here won't be much smaller than this one. They'll be about the same size. So the volume of, say, this orange shape, so volume number 2, because here's 1, 2, is approximately equal to the area of that guy right there, this backwards orange shape, times the height, which is delta x. Now, of course, that's not exactly true because it's not exactly the same shape all the way through there. That shape got smaller, the trapezoid got smaller, but it's approximately equal to that if delta x is small enough. If we only have a little tiny delta x here, if this is my delta x, then this trapezoid's not much smaller than that. So we can kind of pretend that we have the same shape all the way through. And then, of course, what we're going to do, because this is calculus, we're going to take a limit as delta x goes to 0, and that approximation will get closer and closer to the actual volume. So we are going to theoretically take some shape, some volume here, break it up into n different little slices here of volume. Then the volume of each of these slices will be approximately the cross-sectional area at that particular place. The cross-sectional area is going to be a function of x. The area here is different than it is back here. So the volume will be approximately cross-sectional area times delta x. If we add up all those little volumes, we'll get approximately the volume of the entire thing. And then this is calculus. We take the limit as n goes to infinity, which means we're taking an infinite number of little slices here. That's the same thing as saying delta x goes to 0. So these little slices here are getting smaller and smaller in length, which makes all those little approximations better and better. It's exactly what you did in Calc 1 with Riemann sums. And then that approximate will change over to an equal. This sum, which is the Greek letter S, will turn into a letter S. That's all an integral is. It's the letter S stretched out. And that approximate turns into equals. So this is how we are going to find the volumes of three-dimensional objects that are stretched along the x-axis. The volume will be the definite integral from a to b, from our starting to our ending point, of the cross-sectional area that's a function of x. That's not a times x, that's a of x dx. And this is called the slicing method. So you can read this here. Okay, so let's look at an example. We are going to prove or derive the formula for the volume of a pyramid. Like you may have learned this back in 8th grade, volume is 1/3 area of the base times the height. We're going to prove that. So I've got some pyramid here, has total length h, total height h. The base of the pyramid is a square where each side has length a. Then, what we're doing here is we're building a Riemann sum. We're slicing this up into little rectangular prisms that are not completely rectangular because the sides are slanted. So we've got some little delta x here. And we're going to add all those up. We're stacking a bunch of these up. We take the limit as delta x goes to 0, and each of these approximations gets better and better. So the total volume will be the integral from 0 to h, from my start to my end, of the area, the cross-sectional area at location x dx. So I've picked some random location x. X is a variable here, but for the moment it's fixed. I need to find how big this area is at that location x. A here depends on x. So we're going to do that using some similar triangles. So if I just kind of slice through here, if I look at this triangle right here, so I'll try to draw it in here. I'm looking at this triangle here. This side is A. The entire side is A. That's, I guess I lied to you. I guess I'm looking at this triangle. This entire side is A. This entire side is H. We're a distance X away. I want S is what we're calling that area right there. Well, S is this side. The area then, that's a square, will be S squared. Okay, so we're going to use similar triangles to find the length S here. So S relates to A. Here are my similar triangles. This triangle here and this entire triangle here. So from the smaller triangle, S is the same as A compared with X, the height of the little triangle, compared to the height of the big triangle. S over A is the same as X over H. You're going to be playing this game a lot in this class, using similar triangles to find something, cross-sectional area or something that's happening at some location X. Okay, it's S we're looking for. So just multiplying the A over, we get S. This side here, which depends on X, is AX over H. So then that cross-sectional area at location X will be S squared, which is A squared X squared over H squared. Okay, then by what we've already determined, this is always going to be true when we're doing this slicing method. The volume is the definite integral from your start to the end, your cross-sectional area at location X dx. We just found this, so we're going to plug it in. So that's A squared X squared over H squared. A and H are constants. This is an integral, an antiderivative of X dx. The constants can come out front. Antiderivative of x squared dx is x cubed over 3, and we're going to evaluate from 0 to h. At 0, everything is 0. At h, we get, oh, we already knew that formula. So the volume of a pyramid is 1/3 a squared. H, where H again is the height of the pyramid, and A here is the length of one of the sides of the square base. Okay, that's a good place to stop in this.